So we've been here on Earth for a few billion years, coasting on our star's stable energy output. But what happens when that stops? The sun's eventual demise has been predicted with alarming accuracy, but its exact nature remains shrouded in mystery. The sun's consistency is one of its most remarkable traits. It's been shining with unwavering dedication for nearly 5 billion years now. That number sounds absurd until you realize that's longer than human civilization has even existed. The implications are staggering. The sun has been a constant in our lives, providing energy and light to Earth while we've been evolving, building societies, and questioning the meaning of it all. But what does this consistency mean for its eventual demise? Some argue it's a sign that the sun is running low on fuel, that it's just waiting for the inevitable, but I'm not so sure. There are still plenty of unknowns about the sun's internal mechanics, and its ability to surprise us time and again only adds to the mystery. What will happen when this consistency finally falters? The sun's demise will have an undeniable impact on our planet. But it's strange that we spend so much time discussing its eventual death without considering what that means for us. We're not just talking about a drastic change in our climate or the collapse of ecosystems, although those consequences are certainly dire. The fundamental question is, what kind of species will we be when the sun expands into a red giant, engulfing Mercury and Venus? Will we have reached the stars, or will we still be clinging to Earth as it's consumed by the very star that gave us life? The possibility that our existence might be intrinsically tied to the life cycle of our solar system raises unsettling doubts about our place in the universe. And yet, despite these existential concerns, humanity seems more focused on developing strategies for mitigating the sun's effects than on contemplating the deeper meaning behind its eventual demise. The sun's heat, it's hard not to take it for granted. We're talking about an object that's been radiating energy in our direction for nearly 5 billion years now. That number sounds absurd until you realize it's a necessary evil, the very thing keeping life on Earth possible. But what if I told you it's also a double-edged sword? The sun's heat is what makes our planet habitable, yet it's also responsible for stripping away its atmosphere and making it inhospitable to any potential life beyond. It's a paradox that challenges our understanding of how the universe balances its competing forces. What does this say about the delicate dance between a star's power and the needs of its planets? When we talk about the sun dying, it's easy to get caught up in the grand finale, the supernova explosion that will signal its demise. But what about the slow fade, the cooling of a star that's been burning bright for 5 billion years? That's where things get really interesting. Because as the sun's energy output dwindles, our planet's climate will undergo a radical transformation. The most immediate consequence is a drop in temperature, and I mean a significant one. We're talking 50 degrees Fahrenheit, give or take. Now, that number sounds absurd until you realize it would make the difference between a balmy summer day and a chilly winter morning almost negligible. But what's really concerning is how this cooling will affect our oceans, which are already struggling to absorb excess carbon dioxide. The increased albedo effect, more sunlight being reflected back into space, could potentially send global temperatures plummeting even further. Of course, this all assumes we don't have some sort of advanced geoengineering solution in place by then. The sun's demise is often seen as a singular event, but its fate is actually part of a broader cosmic trend. Most stars will eventually exhaust their fuel and expand into red giants, just like our sun is expected to do in about 5 billion years. But that number sounds absurd until you realize it's not unique. Many stars have already undergone this transformation, some even multiple times. This raises questions about the long-term habitability of planets orbiting these red giant remnants. What does it mean for a star like Kepler-22b, which orbits a sun-like star in its later stages? Will it be able to maintain a stable climate amidst the stellar turmoil? The answers are far from clear-cut. As we stand on our tiny blue planet, bathed in the warm glow of our star, it's easy to forget that even the sun is not immune to decline. In about 5 billion years, the sun will exhaust its hydrogen fuel and move into a phase known as the helium flash, where helium fusion briefly ignites in its core. That number sounds absurd until you realize that this fleeting moment of increased energy output will be the last spark of life-giving warmth our planet has ever known. The implications are staggering. Temperatures will plummet, oceans will freeze, and any remaining life on Earth will struggle to survive. But what's perhaps most surprising about this impending catastrophe is that it's not a sudden event, but rather a gradual decline. It raises questions about the very fabric of time itself. Can we really say that 5 billion years from now is just as distant from us today as the moment of our birth? Or does the passage of time warp and distort in ways we can't yet comprehend? That's right, folks. We've been talking about supernova and solar collapse, but there is another possibility, one that's often overlooked in favor of more dramatic scenarios. What if simply fades away? I know it sounds absurd at first, but bear with me for a second. The sun is already about 70% exhausted, its fuel dwindling as we speak. If this trend continues, the sun will eventually reach a point where nuclear fusion in its core becomes too slow to sustain itself. At that point, the sun would slowly shrink, with its outer layers drifting into space while the core remains behind. It's a remarkably almost doubling compared to the supernova. But here's the thing, we don't know for sure what this transition will look like, or even if it'll happen at all. The sun's life cycle is still shrouded in mystery, and our understanding of its eventual fate is far from complete. The sun's eventual demise, that's a given, but the exact timing and manner of its passing are shrouded in uncertainty. Take the case of red dwarfs, for instance. These small stars live longer than their larger counterparts, but end up burning through their fuel much more slowly. That number sounds absurd until you realize it means they are likely to burn out only after a few trillion years, long after our own sun has already gone dark. Yet, astronomers still debate whether red dwarfs are capable of supporting life throughout their extended lifespan. It's as if the universe is playing a game of cosmic hide and seek, with us hiding its secrets behind layers of probability and uncertainty. What does this unpredictability say about our understanding of stellar evolution? Is it a testament to the complexity of celestial mechanics, or just an admission that we still have much to learn? Now, let's talk about nuclear fusion, the process that powers our sun. On its surface, it sounds like a straightforward energy source. Hydrogen atoms combine to form helium, releasing a tremendous amount of energy in the process. But what's striking is just how long this process has been running. The sun's already burned through half of its fuel since its birth about 4.6 billion years ago. That number sounds absurd until you realize it's still got enough hydrogen left over to sustain itself for another 5 billion years. The question is, why does this fusion reaction even work? What exactly triggers the combination of these atoms at such a precise rate? Scientists are still debating whether it's purely a matter of gravity and density, or if there's some other, as yet unknown factor at play here. So we've been studying the sun's eventual demise for decades now, and yet, one thing remains stubbornly unclear: its final state. The most widely held theory is that it'll exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets in the process. Sounds dramatic enough, but here's the thing. We're still not sure what happens next. Some models suggest it could contract again to become a white dwarf, while others propose an even more exotic fate, a supernova explosion. That sounds absurd until you realize that our current understanding of astrophysics can't fully account for such massive stellar outbursts. Meanwhile, other theories abound, like the helium flash scenario, which would see the sun briefly double in size before settling back down. And then there's the elephant in the room. What becomes of its core? We may have a few ideas about how stars die, but when it comes to the specifics, we're still flying blind. So we wait with bated breath for further observations and simulations that might shed some light on the sun's last gasp. But until then, one thing's certain: its ultimate fate remained as mysterious as ever. The sun's magnetic field might seem like an afterthought in all this cosmic drama, but bear with me, it's about to become a crucial player in our understanding of what happens when the sun dies. Now, I know some of you might be thinking, magnetic fields are just a bunch of invisible lines that crisscross the universe. But trust me, this one is different. The sun's magnetic field is so strong it dominates the entire solar system, and yet we still don't fully grasp its role in the sun's life cycle. That number sounds absurd until you realize the sun's magnetic field is actually 1 million times stronger than Earth's. What does that even mean? It means the sun's magnetic field has been sculpting the planets around it for billions of years, and that influence will continue to shape our solar system long after the sun exhausts its fuel. But here's the thing. As the sun continues to age, its magnetic field is expected to weaken. The question is, what will happen when it finally collapses? Will it send shockwaves throughout the solar system? Or will something entirely unexpected occur? As we peer into the cosmic archives, we find that ancient star deaths can give us valuable insights into our own sun's eventual fate. The earliest stars in our universe were massive and short-lived, burning through their fuel at an alarming rate. Their explosive ends left behind remnants like pulsars and neutron stars, which still echo with the residual energy of their demise. What does this tell us about our own star? That it too will eventually exhaust its fuel and shed its outer layers, but perhaps not in a sudden, cataclysmic event. The time scales involved are mind-boggling, millions to billions of years, and yet we're still grappling with the question, what constitutes a normal death for a star like our sun? Is it a gradual decline or an inevitable supernova? We can't help but wonder how this pivotal moment will shape the future of our planet and whether we'll be here to witness it. The prospect of human civilization surviving the sun's demise sounds more like a thought experiment than a genuine possibility. But let's indulge in it. Assuming we have a few centuries warning, and that's a big assumption, given our current understanding of astrophysical events, would we be able to adapt? The answer hinges on one crucial factor, the type of supernova the sun will likely become upon its eventual collapse. If it's a relatively gentle type I, Roman II, or Roman III explosion, we might have a chance, but that number sounds absurd until you realize the actual odds of us developing a sustainable off-world presence in time are probably infinitesimally small. The more energetic type Ib/C supernova pose an existential threat to Earth itself. So, given our current rate of progress and the astronomical stakes involved, the question is, can we really imagine a future where human civilization not only survives but perhaps even thrives, all while facing such an unfathomably massive cosmic calamity? When we study other stars' deaths, it's not just about understanding distant supernova, it's about grasping our own cosmic fate. I've always been skeptical of theories that rely on extrapolating from single events, but the sheer scale of these starbursts is a different story altogether. We're talking thousands of solar masses unaccounted for, yet somehow they manage to explode in a blaze of light and energy. That number sounds absurd until you realize it's not just about raw power, it's about the mechanisms that govern our universe. What does it say about the fundamental laws that govern matter if entire stars can be transformed into such cataclysmic events? The fact that we still can't fully replicate these explosions in a lab setting raises more questions than answers, but one thing is clear. Understanding how other stars die might hold the key to unraveling our own solar system's secrets. The sun's demise marks the end of an era, but it also raises a far more profound question. What happens next? The universe has been expanding for 13.8 billion years, and yet we still have no idea what its ultimate fate holds. Some theories propose a gradual slowdown, while others suggest a cataclysmic collapse. I'm not sure which one sounds more absurd until you consider the sheer scale involved: billions of galaxies stretching out into the void, each with their own separate fate. It's almost as if the universe is deliberately withholding its secrets from us. And yet, even in the face of such uncertainty, scientists continue to propose increasingly wild scenarios. A multiverse where our reality is just one of many, or the possibility that the cosmos itself is just a simulation. The more we learn about the sun's eventual demise, the less certain we become about what lies beyond. Join me as we delve into the secrets of our star's fate and what it means for our existence in this vast, mysterious universe.